Hello everyone, sorry I can't be here today for your review, but we're going to be going over this, and if you have any questions you can ask anything on Monday when I'll be in class. You'll be having your test on Tuesday. So we're going to go ahead and start. You'll see that we have concept as well as mathematical. Those that are mathematical are going to be the bold-faced items here, and we'll get to those. So let's go ahead and begin with chapter 13. Definition of a fluid and why solids do not meet that definition. Well, fluids are going to be consisted of both liquids and gases. And the definition of a fluid is it's going to flow. It doesn't have a defined shape. Solids have a defined shape, but liquids and gases are in the shapes of their containers. And they can't really be contained. So flowing and no shape. Those are the criteria of meeting a fluid. Definition formula for pressure. Okay, pressure in the English system is PSI, pounds per square inch. So we have the pounds on the top, and we have the inch squared on the bottom. In the metric system, it is going to be pascals. And a pascal, a pound is a force, so we're going to have our newtons, and instead of inches squared, we're going to have meters squared. You're going to have a mathematical problem where you'll need to convert from PSI to pascals, just like we did with the foot pressure lab. So we're going to be starting off with a pounds per square inch. So you have pounds per square inch. And we need to cancel our inches and convert into the metric system. We need to get to meters, so we first need to go to centimeters. You'll have the unit converter, that 1 inch, or 1 inch, is going to be equal to 2.54 centimeters. But this is inches squared, so we need to square this, and therefore we need to square that as well. So the inches are going to cancel. Now I need to convert my centimeters to meters. So I have centimeters to meters. 1 meter is composed up of 100 centimeters. So again, I need to square both of those. And again, when you're doing this, you're squaring the unit and you're also squaring the number. So in this case now, my centimeters are going to cancel, and I'm now in my meters squared, which is desired for pascals. So now we need to convert from pounds to kilograms. So we have to multiply by 1 pound is going to be equal to 0.45 kilograms. My pounds will cancel, and now I'm in kilograms. So I have a kilograms, but I need a newton. If you remember, newton is a force, which is a mass times acceleration. We have a mass, which is kilograms, but we have to multiply it by acceleration. So this has to be multiplied by 9.8 meters per second squared. And that will get us into pascals. Why your ears feel pressure at different elevations, where is pressure higher, and what's happening to your eardrum, and how yawning or swallowing resolves the pressure difference. So if you're going from a high elevation to a low elevation, okay? Let's say you're going from a low elevation, so you're at sea level, and the pressure at sea level is going to be high. So you have high pressure because you have more atmosphere pushing down on top of you. And going down to, or going up to a higher elevation, you're climbing a mountain. So your higher elevation, your pressure is going to be low. Okay, so if you're going from a high pressure to a low pressure, if you remember your ear, so our ear has the eardrum, here's the eardrum, and we're starting off, if you're going from high pressure to low pressure, so we're going from a lower elevation, we're climbing the mountain. Outside, we start off with high pressure, and inside we start off with high pressure because we are at sea level. The inner ear has this high pressure. And as you start to climb, the pressure is going to drop. and you have lower pressure on the outside. So what happens is your eardrum is going to be bending outward from high pressure to low pressure. How do we equalize that pressure? We need to open that eustachian tube. You need to yawn or swallow, and this opens up that tube. You don't need to know the name, it's a biological term. Opens up the tube that's in your throat to equalize that pressure. So the reverse would be true. If you're going from a low pressure to a higher pressure, if you're coming down the mountain, okay, so if we're doing the reverse, if you're going from a low pressure to a higher pressure, what's going to happen is you have your lower pressure in your inner ear, the outer becomes higher pressurized, and then the eardrum will actually bend inward. So you know the direction that the eardrum is bending depending upon which direction that you're going, and how to resolve this. 2 reasons why it's difficult to breathe at higher elevations. So the 2 reasons, first one is there is less oxygen at those higher elevations. Also, as we discussed here at the higher elevations, there's also less pressure. So the combination of those 2, you have less pressure pushing in. So your lungs need to expand more. Lungs need to expand more. So as you travel up in the atmosphere, you get fewer and fewer air particles. At about 15,000 feet, you have about half of the oxygen. And so you need to actually breathe in more. But also you have less pressure pushing the air into your lungs. So you really have to use your abdominal muscles to really suck in that air. Pascal's principle, this is the toothpaste concept. Doesn't matter where you squeeze, the toothpaste is still going to come out. And that's because the force is going to be transmitted. Force will be then transmitted through the fluid. So that force is going to be transmitted through the fluid, and it's going to be evenly distributed. So all the particles will be experiencing that same force on the inside of the fluid, and then the toothpaste will then shoot out. Calculate the force from hydraulic pressure and the relative displacement. There's going to be 2 parts to this question. So remember that with Pascal's principle, the pressure is going to be the same on both sides of a piston. So you have pressure 1, you have pressure 2. Pressure is equal to force over area. And if we're trying to calculate the output force, we multiply both sides by A2. So your output force is going to be equal to the input force times the ratio of the areas. And your area is going to be larger for the second one. So we're going to have a larger output force. So if you remember, work is equal to force times distance. So we have the force 1 times distance 1 going to be equal to the force 2 times the distance of 2. So what's happening is our output force is going to be increased. Your input force is going to be decreased. These have to be equal to each other. We can't get more work out of the system. So in order to accomplish this, you have to have a high amount of movement on the input distance, and the output distance is going to be less. if you remember the thumb wars, we had a 1 milliliter fighting a 30 milliliter piston, and you had to push that 1 milliliter piston all the way in, that long distance. It had to be moved. So we had to move it in a long distance, but a very minimal input force. And what it did, it pushed out the 30 milliliter piston with a larger force, but the distance that it moved was very, very small. So you're getting a larger output force by moving a small distance. Also, when you have your jack for your car, you're moving the lever a large distance, and it pumps up the car with a large force, but it moves the car up incrementally in small distances. Bernoulli's principle and how velocity affects pressure. Major concept of Bernoulli is if you increase the velocity, you're going to decrease the pressure. So we had many instances where we had an airplane wing, for example. The air hits the wing and it travels over both the top and the bottom. And then the air comes back and then continues. However, we have to travel a larger distance on the top of the wing compared to the bottom of the wing. And so, since we're traveling a longer distance in the same amount of time, it increases the velocity. So on the top of the wing, we increase the velocity, therefore we decrease the pressure, according to Bernoulli. And so we have lower pressure on the top, and we have higher pressure down below. That provides a lift force due to the difference in pressure. So we get this lift for the airplane. Why cups come together when air is blown between them? Same principle. We're blowing the stream of air in between the two cups. We are increasing the velocity between them of the air. Therefore, it's going to decrease the pressure. So it's going to be lower pressure on the inside between the two cups. It'll be higher pressure on the outside. The higher pressure wants to equalize by pushing to the lower pressure, and so the two cups are then going to move inward. We may have deleted this concept from lecture. I'm not quite sure, but we'll go over it right now. We went over it in chemistry, but we'll go over it again. Why does a liquid stay in a straw when you cover it with a finger? So imagine you have a straw. You've done this maybe at restaurants. Here's your straw, and here it's filled with liquid. So it's filled with a liquid, and what happens is it forms a drop down at the bottom. So some of the fluid actually drops down. So you cover this top and you bring the straw out of the fluid, and some of the liquid actually drops down. So it was initially here, but now it has dropped a little bit due to gravity, pulling this liquid down, and it forms this drop. Well, what's actually happened to the volume of air on the inside of the straw? We increase the volume of the air. So this is not velocity, this is volume. You increase the volume of the air because, again, the drop has fallen, and so therefore this has fallen. So the air has actually expanded. We've increased the volume. If you remember from chemistry, what happens to the pressure in order to accommodate an increase in volume? This is the Nerf ball. If you apply pressure to a Nerf ball, if you increase the pressure, you decrease the volume. If you decrease the pressure, you increase the volume. So since we've increased the volume, it lowers the pressure on the inside. Remember, pressure and volume are inversely related. So we've got lower pressure on the inside here now, and it's actually higher pressure underneath, and the higher pressure helps to push up the liquid to try to equalize that. Why a ping pong ball stays in the air at an angle or under a stream of air. We put a ball in a stream of air from a vacuum cleaner. So here is the ball. And because we have this stream of air going like this, we've increased the velocity and we've lowered the pressure. So it's lower pressure on the inside. And if the ball begins to drop due to gravity, the higher pressure will push upward to keep it in place. And the same thing, if it tries to get blown upward due to the airflow, the same thing will happen. It's got higher pressure on that side as well. So the higher pressure will push it down. It'll keep that ball floating in that angled air column. What causes warm water to pool on the west coasts of the Americas? We didn't go over that, so I think we're going to cross that off. So going to the net effect of expansion of materials when heating and proportional to temperature and length of an object. So when you increase the temperature, things are going to expand. Remember, solids are going to expand. It's going to increase the length proportionally. Proportionally. Okay, so if you also double the size of that material, like if it's a rod, for example, if you double the size, you're going to double that expansion. So those are the two principles. So if you double the temperature, you're going to double the expansion. If you double the size, you'll double the expansion as well. So there's going to be two formulas. Calculate the expansion of an object in length using coefficient of linear expansion. So calculate the expansion. So this is going to be the change in length. Okay, and this is going to be equal to L1, it's going to be the original length, times the coefficient for that material, times the change in temperature. Okay, now if it's asking for what is the final length, you have to say, well, this change in length is L2 minus L1 is equal to L1 alpha delta T. And if it's asking what the final length is, then we have to add the initial length to both sides. So the initial length, L1 plus L1 alpha delta T. Calculate the expansion of an object for volume. So similar formula, you have delta V is going to be equal to the initial volume. The change in volume will be the initial volume times beta, which is the coefficient for liquids, times delta T. This will give you the change in volume. If it's asking for the final volume, it's going to be V2 minus V1 equals V1 beta delta T. If we want the final volume, we have to add the initial volume to both sides. So V2 would be equal to V1 plus V1 beta delta T. So each of these problems might be asking for the change in length or the expansion, or it could be asking for the final length or the final volume. Definition of plasma. and examples where to find plasma. Plasma is high energy ionized gas. So in the lights in this room, we have plasma. We have a current running through it, and it stimulates those gases to glow. Where do you find plasma? We find it in the sun. We find it in lightning. And you find it in neon lights as well as lighting in a room. That finishes chapter 13. On to chapter 14. Definition of a wave. Remember, we had people standing creating waves on a rope, and there was a card that was taped to it, and the card was moving up and down, up and down, up and down. The wave was moving along the rope, but the card never moved up and down or away from that up and down motion. So the net motion of the card was zero. So definition of wave, it's a propagation of energy. We have a propagation of energy. So if you throw a pebble into a pond, it creates those ripples. The water particles at the source of where the pebble hits the water, those water particles stay where they are, as do all the water particles do in the water. It's the ripple, it's the energy that moves outward from that. So it's the propagation of that energy, and it is not a transport, of material. It's not moving the material. It's not moving that substance. Difference between longitudinal and transverse waves. We did longitudinal first. We did trans first. So trans means going across, like transcontinental. This is when the pulse that you're giving it, if you remember with the rope, the pulse was the energy, it was moving it up and down, and the wave was being propagated in a perpendicular direction. So pulse is perpendicular to the direction of that wave. We then did a longitudinal wave where we used a slinky, and we pulled the slinky out, and the slinky moved in the same direction. So a longitudinal wave is going to be the same direction as that pulse. Okay, on to the other side. Okay, let me see if we're set here. Okay. So continuing on, well, what is a pulse? The pulse is the energy input for a wave. Definition, draw and label a crest and a trough. So if we can do a couple of waves like this, do your best. Okay, the crest is going to be the top of the wave. The trough is going to be the bottom of the wave. So we've drawn, we've labeled, and defined the crest and trough of the wave. Definition, draw and label a wavelength. A wavelength can go either from crest to crest, or trough to trough, or really anywhere where it's going to repeat the wave again. But typically it's from crest to crest, or from trough to trough. And it's the lambda, it's the length of the wave. Definition of a period: it is the time for one wave to repeat itself and it is measured in seconds. So when the one wave repeats itself, when it repeats, this is called an oscillation. If you remember, an oscillation is, it goes there and back again, just like a pendulum. So a pendulum goes there and back again. That's one oscillation. The wave goes down and then up again, or it goes up and then down again. It's the time to repeating itself. So that's going to be an oscillation. And it's measured t. Time is measured in seconds. And it's also the inverse of the frequency. If you remember, frequency is measured in hertz. And a hertz is actually equal to 1 over seconds. It's the number of waves per second. So the inverse of the inverse is the thing itself that will give you units of seconds. So 1 over hertz will give you actually seconds, because hertz is 1 over seconds. It's the inverse of the inverse. Okay, so period is measured in seconds. It's the time for one wave to repeat itself. Definition and calculation of frequency. So it's going to be, how often does this wave occur? How often a wave occurs. Okay, so this is going to be measured again. It's the number of waves per second, and the frequency will be equal to 1 over the period. It's the inverse of the period. So we did a couple examples in our lecture where we had one wave repeating once every second, but we had a wave that was coming in every half of a second. Okay, so if it was coming in every half of a second, that's the period. Okay, well, what's the frequency? Well, if it's coming in every half, the inverse of 1/2 will give you 2. So the frequency of the wave would be 2 waves per second. If you have a half a wave coming in that time period, okay, or if it takes a half a second for the wave to complete itself, then if you have 2 waves, you have 1 second. Definition, draw, and label amplitude. Amplitude is the height of the wave. So it's the height of the wave from rest. So from the middle. So if we can draw it over here, so if this is at rest, then here, let's draw a wave going like this. Okay, we can have a higher amplitude looking like this. So this has increased the amplitude, but notice how the nodes are in the same place, so it's going to be the same frequency. So make sure you distinguish between amplitude, which is the height, and the frequency, which is how often that it occurs. Calculate the velocity of a wave. The velocity is going to be equal to the frequency times the wavelength. And you might need to calculate the frequency by the problem giving you the period. So you might have to use that and plug it in to that. So it might give you the frequency, or it might give you the period, it might give you the wavelength. So then you first have to calculate the frequency and then multiply that by the wavelength to calculate the velocity. Or it might give you the velocity and the wavelength, and you have the frequency, and it's asking what's the period. And you're going to have to plug it into there, or plug it into this one. What happens to the reflected wave when it hits a boundary, such as a different large spring to small spring with the spring or a wall? It's always going to be inverted. Okay, so if it hits a wall, it's going to be inverted. Okay, so you'll have an inverted wave as a reflection. And it's going to be the same amplitude when you hit a wall. Okay, if you have a smaller spring going to a larger spring, okay, so if you have a small spring going to a large spring, okay, that's almost like hitting a wall. What's going to happen is most of it's going to get reflected and inverted. Most will get reflected. If you go from a large spring to a small spring, most of the energy will go into the small spring and a little bit will get reflected. So most is going to go through. Constructive and destructive interference. Constructive interference is when the waves build upon each other. So if you have two waves that are approaching, so this one's approaching this, and we've got another wave approaching in this direction, they're going to be constructive. They will add to each other. We're going to get twice the amplitude. So that's constructive. And the result will be you have a very large wave like that. Okay, that's constructive. We'll do destructive over here. Destructive is when you have canceling of the wave. So if you have a wave coming up down on top and you have a wave coming down below in opposite directions, they will hit each other and you'll temporarily cancel that wave. Okay, so you get amplification and cancellation. So you get amplifying or amplification, and over here you get wave canceling or cancellation. Velocity and refraction of sound waves with variation in temperature and how you hear better at night. So this is the definition of refraction. Definition of refraction is when waves bend due to the density of the material. So waves bend toward the denser material. How you hear better at night? Well, here's your sound source, and here's the ground. Remember, during the day, you get hot temperatures very close to the ground because the visible light comes into the ground. It turns into infrared heat, and so our hot temperatures are going to be close to the ground. At night, we lose our heat source, and so all the heat's been rising. You actually get warmer temperatures up above. You have warm, and then you have cooler temperatures down below. So what happens is, if a sound is going straight out in both ways, it's going to bend toward the cooler or the denser material. So your warmer is going to be less dense, and the cooler will be your denser. And so your sound will stay near the ground rather than during the daytime when it goes up more into the air. Reflection of light. Definition, normal angle of incidence and angle of reflection. So your angle of incidence, here's going to be your theta. This will be your theta I. And you have your angle of reflection. Here's your theta R. Okay, and what we have is, if you have a mirror down below, your normal is going to be perpendicular to the surface. So this is your normal. And if you have a material or light coming in at an angle of 20 degrees, so here's your angle of incidence, and this is going to be, we'll say it's 30 degrees. And if the angle comes out at 30 degrees, then this is going to be your reflected angle. So the concept of reflection is the angle of incidence is going to equal the angle of reflection. The angle that comes in is the angle that comes out. Remember, it's respect to the normal and not the surface. So if it's coming in at a 30-degree angle, it's right here. If it's coming in at a 60, it's here. If it's coming in at 80, it's right here. So it's always with respect to the normal. So if it comes in 30, it's going to go out 30. If it comes in 20, it's going to go out 20. And diffraction. This is when waves bend due to a barrier. Waves bend due to a barrier. This is the water table that we did. And if you remember, we put through, here's our ruler, we moved it, and it pushed the water, and the water felt the edges here, and it slowed it down. And so we got this bending of the wave. So the middle portion didn't feel the effects of the friction of the object that was blocking the water. And then that created some interesting patterns that looked like this, where we saw some shimmery types of water, where we had amplification and cancellation. So it's when waves bend due to a barrier. So when waves come in from the ocean and they bend around a point, it's due to diffraction. Chapter 15, this is dealing with sound and music, sound waves. So sound as pressure waves and pushing of molecules due to vibrations of objects. So it's all due to the vibration of everything, whether it's the strings of an instrument or it's your vocal cords. And if it's a tuning fork, if you remember the tuning fork, okay, what's happening is this is vibrating. Those are my symbols for vibrating. And since these are vibrating, it pushes the air next to them outward. These particles then go and they can bounce and hit other air particles. And then those will then hit other air particles as well. More and more air particles will get hit as you have a larger radius, and you're going to be losing energy from that. So as you lose energy, what will happen is the sound will dissipate in distance. So the speed of sound in a solid, liquid, and gas, and what the speed depends on. So if you remember, this is due to the density. It's the density of the material. With solids, the particles are closer together. So your particles are closer. And because the particles are closer, the energy is transmitted a lot faster. With gases, your particles are more spread apart, so it takes time for it to bump into the next molecule. So with solids, we have the highest velocity, and with gases, we have the lowest velocity. Amplitude is detected as loudness in decibels for each 10 decibel increase. So when you are going, for example, from 10 decibels to 40 decibels, remember, every 10 is going to be perceived as twice as loud. So from 10 to 20, it's twice as loud. From 20 to 30, it's twice as loud. From 30 to 40, it's twice as loud. So we have 2 times 2 times 2, so it's going to be 8 times as loud when you have a 30 decibel increase. Pitch is synonymous with the frequency. This is the tone of the note. So if you have a low pitch, you have a low note. Okay? If you have a high pitch, you have a high note. So a high note, you have a high frequency. A low note, you have a low frequency. The Doppler shift in frequency of waves when moving toward or away. So if you have an object with a velocity that's moving along, if this object was stationary, it would be emitting its sound waves, and the sound waves would be the same on both sides of the object. But now that it's moving, those sound waves are going to get compressed on the side in the direction that it's moving. And over here, the sound waves are going to be farther apart. So the person who's standing over here, as the object's coming towards them, is receiving the sound of the object, but also it's being pushed faster because of the movement of the object, so you get these faster waves. If waves are coming to your ear faster, it's going to be increasing the frequency, which of course will increase the pitch. If you're on this side of the sound, the waves are going to be coming to you slower. So you have these slower waves. And the slower waves will mean you have a decreased frequency, you'll have a lower pitch. Timbre is the sound quality of the instrument, whether it's your voice or whether it is an actual instrument that you're playing. The sound quality, and it's due to the material. So a violin and a flute can each be playing a C, but they will sound very different because of the materials that are producing them. Difference between consonant and dissonant. Consonant is a pleasant sound or a happy sound. Okay, dissonant is, it's dis. It's an unpleasant sound. So you have an unpleasant sound. So again, these are pleasant sounds. These are unpleasant sounds. Remember, if 2 notes are too close to each other, it's not a very good mathematical ratio. It sounds very off to our ear. It's a very unpleasant sound. And why are beat notes produced? Remember, if you have 880 versus 883, you've got a frequency that's like this. And if you can imagine having a higher frequency like this, so the waves are coming in faster, okay? So here, they amplify. There, it's going to be loud. Here, they cancel. it's going to be soft. We get constructive and destructive interference. Here again, they are going to amplify. It will be loud. So when they're opposites of each other, it's going to be soft. Where they are overlapping, it's going to be loud. So you have this repetitive loud, soft, loud, soft, loud, soft. Okay, so we could probably go like this, and this would be soft again. And this gives you a fluttering sound or a pulsing sound. So it's pulsing or a fluttering sound. That is it. If you have any questions, please bring them to class. Hopefully you're able to see this. I'm just going to zoom out just a little bit in case if you need to put a couple of words. Okay, and I'm going to zoom out from the front page as well in case if something was not seen as well. That's it. Good luck. We'll see you when I see you.